Welcome back, physics students. Today we're going to start our new unit known as simple harmonic motion. It's a unit that's very mathematical, so my guess is that most of you will appreciate, if not actually come to like this unit. It is quite short. We are going to do 3 days of notes and then one fairly short homework assignment following the 3 days of notes. Um, Probably the best thing to do is to print the note packet out. You'll find it in the simple harmonic motion folder. And you can take notes right on the handout. And if you don't have a printer, no worries, just grab your notebook and follow along. And as we write definitions and work examples, feel free to hit pause at any time so you can work things out at your own pace because I'm going to move quite quickly through the slides. And depending on the pace that you want to move at, you can just hit pause as you need to. So simple harmonic motion is going to bring back many of the concepts that we covered in the waves unit. For example, simple harmonic motion basically comes from the oscillation of objects. Not all oscillatory motion is going to be simple harmonic motion. There's a very specific definition of simple harmonic motion that we will get to tomorrow in the next video. But for today, we're just going to discuss some various types of oscillations. And then tomorrow, after we meet the definition of exactly what is simple harmonic motion, we'll come back and talk about which of these that we meet today would actually meet the criteria to be SHM. So some examples of oscillations. One would be a mass on a spring. So if you were bungee jumping and you jumped off a high structure and the elastic cord caught you, you would begin to oscillate up and down on a spring. Or on an elastic cord. Now that's clearly an oscillation. Does it meet the requirement of simple harmonic motion? Well, I don't know. We'll see. We'll talk about that tomorrow. Probably the most classic example is that of a pendulum. If you take a pendulum, this is its equilibrium position down here. If you displace the pendulum away from its equilibrium position and then let it go, it's going to begin to oscillate back and forth. It will speed up, it will slow down, it will sometimes cross through the equilibrium position, sometimes it will be out at the extreme positions. And it's that motion that we're going to try to model with sine and cosine functions. So we're going to be writing equations that will tell us where the pendulum bob is, how fast it's going, and what its acceleration is. I think you'll find it to be pretty interesting. An object bobbing up and down in the water, if you took a block of wood and you pushed it down in the water and let it go, it would oscillate upward due to a buoyancy force. And it's definitely oscillatory. The question is it simple harmonic motion? Well, we'll talk about that tomorrow. A diving board or a cantilever, if you jump off the board will continue to vibrate after you jump off it. That's an example of an oscillation. Musical strings, we had the air columns vibrating when we did tubes and strings. We had air oscillating inside the tubes. We also had strings vibrating when we did stringed instruments. So those are examples of oscillations. And then we have the classic S&P waves from earthquakes. All of those represent examples of oscillations, and we'll, again, talk about these tomorrow as to whether or not they meet the requirement for simple harmonic motion. Going back to one of our waves facts, actually, we learned this in the very first day of waves, that waves transfer energy without matter. Right? That was a multiple choice question on one of your tests, I believe. And basically, at the source of all waves, there's going to be an oscillating object. So in this particular case, if your hand is oscillating up and down, that oscillating hand will lead to the spring wave that's traveling off to the right. You could have a tuning fork with the tines vibrating back and forth. Those oscillating tines will create sound waves. You could plunk your finger in the water at regular intervals, and that oscillating motion will cause water waves to radiate outward. So if you trace any wave back to its source, you're going to find something oscillating, and the same is going to be true in simple harmonic motion. It's helpful if we review a few of the quantities that we met back in waves, and even, yes, back into rotational motion. Our old friend angular frequency is coming back to see us. So we met frequency and period. Hopefully you're quite familiar with those. The symbol for period is capital T, and period is measured in seconds. And on your waves reference table, hopefully you have written that period is the time for one complete oscillation. And the quick equation we wrote down on the top of your reference table, that period is the number of seconds divided by the number of waves. I know it's kind of painful to watch me write with the mouse. I assure you that it's more painful for me to write with it than it is for you to watch it. I wish I had my smartboard back. And frequency is symbol little f, and the units are hertz, which would be 1 over seconds, right? That would be the base unit for frequency. And it's the number of waves per second. So it's the inverse of this. This is I'm just going to do W, the number of waves per second. And we did quite a bit of that. And you may remember that these two are actually related to each other. Hey, that's a nice bracket with the mouse. Frequency is 1 over period. So they're inverses of each other. If you know frequency, you know period. Hopefully all that makes sense. Then our old friend angular frequency, which as you know is not a W, it's an omega. And omega was measured in radians per second instead of 1 over seconds. But remember, radians is kind of invisible when it comes to units. And we'll take a slightly different look at it here. Our equation is going to be omega is 2 pi times the frequency. So whenever you have the frequency, multiply by 2 pi, and you will have the angular frequency. I wrote that in the wrong column there. Omega is going to be 2 pi f. Now you've got it twice. You'll know it twice is good. All right, just to review the concepts, if we have a pendulum and it completes 10 complete swings back and forth in 8 seconds, calculate its period. Well, the period is the number of seconds divided by the number of waves. So that would be 8 seconds divided by 10 waves. Remember, waves and oscillations and all that stuff's invisible, so we would have 8 over 10, which will be 0.8 seconds. Yes, I know this is a review. I hope you're horribly bored right now. That would be a good sign. And to find frequency, we could easily do the number of waves per second, or we could just invert this number. So the frequency will be 1 over the period, which will be 1 over the 0.8 seconds. And when you do that, you should get 1.25 hertz. All right, now, something we haven't done in a while, let's calculate the angular frequency. The angular frequency, of course, omega, not W, is going to be 2 pi times the frequency, which is going to be 2 pi times the frequency we just found of 1.25 hertz. And that, when you multiply it out, should give us about 7.9 radians per second. All right, so let's get a little more specific about the motion and begin to put some variables on things. So the equilibrium position. So if you put a mass on a spring and you don't let it go, don't just drop it. Take it down with your hand and find the point where it's going to stay at rest. When you find that point, you have found the equilibrium position. Then in order to get it oscillating, you have to raise it up some distance up to its amplitude. So we will refer to the amplitude 2 different ways in simple harmonic motion. We'll refer to it as A and also x0. Now I know it's oscillating in the y direction. You'll have to get used to that. In simple harmonic motion, people typically model with x, even though it's oscillating vertically. So the little subscript 0 here, x0, tells us that we're not just here, which would be a regular x value. We're all the way at the top or all the way at the bottom, which would be positive and negative x0. So the average position of the equilibrium position, that's where we talked about right here. That's going to be the position of the object when it's at rest. And then x is going to be basically its particular distance from the mean. So in a particular direction, because displacement, as you may remember, is a vector quantity. So it has a direction as well. So if the ball were located right here, its displacement would be positive, whatever that value would be. And if the ball were down here somewhere, it would be negative, whatever that value would be. But the displacement is going to be where you're located, and that will change throughout a problem as the mass is oscillating up and down. The thing that won't change if it would be its amplitude. That would be the position when it's at its two maximums, the positive and negative maximum. Now, being a scalar quantity, it will be positive only, whereas the displacement will be positive or negative. So when your equation spits out negative 0.8 meters, you know it's below the equilibrium position by 0.8 meters. All right, so there's two different ways to let the mass go. Notice it says initial conditions down here. Sometimes we get a sine function, and sometimes we can model the displacement with a cosine function. The only difference is how you get the system started. So if you start with the mass in the middle and then just kind of flick it with your finger, it's going to start at 0 meters and then begin to oscillate like a sine function. However, like in the previous example where the mass started up at the top, if we were to take this mass, raise it up to the top, and then let it go, and that were the starting position, notice it would be starting up here at the top. So we're going to be using sine functions to model when the system begins at the equilibrium position, and we're going to be using cosine functions to model when the system begins at one of the two extremes, at one of the two amplitude positions. So as it says, a good thing to write in your notes, you're going to use sine to model when it starts at the mean position, and you're going to use cosine to model when it starts at the amplitude position. Hopefully that makes perfect sense. That's really the only difference. Then we actually want to write equations to predict where something is going to be, because what we want is to say, all right, at 3.75 seconds into this oscillation, exactly where is the mass? It might be above the equilibrium position, might be below. We need an equation to tell us. So the function that we are going to use when we start at the mean position, our equation is going to be x equals, and x is what we're looking for. Where is the mass? The amplitude, x0, times the sine of omega t. Now, t is the main argument here inside the sine function, and the omega just sits in front of it. If you remember when we took derivatives yesterday, when we took derivatives, it was this omega thing that kept popping out in front. Another way to write it, if you prefer a instead of x0, but it's really the same thing, x equals a sine omega t. And similarly, should the system start up at the top, or I guess even down at the bottom, we would model with the cosine function. So you would write x equals x0. Remember, x0 is not just any x, it's the maximum position, maximum distance from the equilibrium position, which would be down this center line. So it's either x equals x0 cosine omega t or x equals a cosine omega t. Either one is just fine with me, and they're both wonderful for modeling. All right, so simple harmonic motion is the type of motion that occurs. We have to have a restoring force in order for there to be oscillatory motion. So when you move a pendulum off to the right, gravity wants to pull it back to the left. When you take a mass and you pull it to the right, the spring force wants to pull it back to the left. That's known as the restoring force. It's going to be the force that tends to restore the system back to its equilibrium position. And there's something very special about the force, the restoring force, in simple harmonic motion. The restoring force is always in the opposite direction of the displacement, which makes sense. If you raise a pendulum up and to the right, gravity wants to bring it back to the left. If you displace a mass on a spring to the right, the spring force wants to pull it back to the left. So the force and the displacement are always going to be in the opposite direction. So in general, force is going to be proportional to the negative of the displacement. So if x is positive, the force will come out negative. And if the x is negative, the force will come out positive. Hopefully that makes sense. Since the force is proportional in the opposite direction as the x, that means the acceleration must also be proportional to the negative of the displacement in the x direction. That's in general. Now, when it comes to a spring, you may remember how F relates to X. It's called Hooke's law, and we'll write Fs equals Kx. Except we're going to put a minus sign in front of it, which the Regents reference table, that's very sloppy. The Regents reference table doesn't have it, but the AP reference table, if you take a glance, says Fx equals negative Kx. Now, the negative really doesn't mean all that much, except it's reminding us that when you have a positive x, the force is going to be in the opposite direction. It would be in the negative direction. So that little negative sign right there helps to keep the sign on the force true and pointing in the direction that it actually should. And the acceleration, which will be the force over mass, right? Newton's second law would be negative kx over m, because acceleration is always force over mass. But the key here on this whole slide is that the restoring force is always in the opposite direction to the displacement. All right, one more slide, and your page might be in landscape mode, so flip that over portrait so we can do some notes here. And here we have a mass on a spring. Somebody has displaced the spring out to the right, and when we let it go, it'll zip back to the left, and then back to the right, back to the left, back to the right. That's the nature of simple harmonic motion. So what we're going to do is we're going to fill all these boxes in with positives, negatives, or zeros, because we want to start to get a handle on when a object is in a particular location, which way does its force point, which way does its acceleration point, and which way does its velocity point, because those are all three different vector quantities, actually four vector quantities if you count displacement, and we care about which way they point. So we're going to consider off to the right to be positive territory and off to the left to be negative territory. In each of these boxes, we're going to put a positive, a negative, or a zero. So let's take the mass, pretend we've displaced it out to here, out to x0. Notice the x0 down there. We've taken it all the way out to its equilibrium position, so we're going to say it's displaced in the positive direction. Now, which way is it moving? I wish we were in class. If we were, I would have a mass on a spring oscillating in front of you to distract you the entire time that I'm teaching about this topic. And you would watch the mass going up and down, and you would quickly learn that whenever the mass is at its extreme positions, it is, at least for a moment, at rest. So the velocity out here will be 0. And when it's displaced to the right, which way does the restoring force point? Well, as we learned on the last slide, the displacement and the restoring force always need to be in opposite directions. So as we fill this slide in, we're hoping that columns 1 and 3 will always be the opposite of each other. And the force and the acceleration, if you think about Newton's second law, should always point in the same direction. So if the force is in the negative direction, that means it must be accelerating in the negative direction. And if you think about it, the mass is going to begin, because the force is pulling it to the left, it's going to begin accelerating to the left. All right, so then the mass continues to the left, and then it crosses through the equilibrium position. Now, it's going quite fast when it gets to the equilibrium position. It's not stopped. It's only stopped when it's out here at the extremes, both to the right and the left. So which way is it displaced? Well, it's not displaced at all when it's at the equilibrium position. Which way is it moving? Well, it's moving in the negative direction. And does it have a restoring force? The only time it doesn't have a restoring force is when it doesn't have an x. Fs equals kx. So at that point, we have no restoring force and we have no acceleration. although it's going really fast there. This is going to be the maximum speed is when you go through the equilibrium position. Now, when it gets all the way to the left, it's going to be somewhat similar to row number 1 here. When it gets all the way to the left, its displacement is in the negative direction. It won't be moving at all because when you're at the extremes, you're not moving. And the restoring force is trying to pull you back to the right. As soon as you're displaced to the left of the equilibrium position, the force tries to return you to the right. Notice, as predicted, columns 1 and 3 are in the opposite direction. And the acceleration, well, if the force is pulling it to the right, it's going to be accelerating to the right. And then it's crossing through the equilibrium position here, so it's not displaced at all at that moment right here, but it does have a velocity. It's now heading back to the right. And I know, even though we had zeros there and there, there's a complete difference. The velocity here was to the left, and the velocity here is to the right. So hence the positive that we got right there. Now the restoring force, well, there is none, because when you have an x of 0, you have an fs of 0. Therefore, we have an acceleration of 0. So hopefully that chart helps the notion of a restoring force, displacement, and which way the particle is moving. 3 quick questions here, and then we'll call it a day from the note perspective. So when is the velocity of the mass at its maximum value? Well, we discussed that. When its displacement is 0, meaning when it's going through the equilibrium position. Second question, when is the acceleration at its maximum value? Well, A would be at a max when the force is at a max. When is the force at a max? When it's at the extreme positions, when it's out at x0 or negative x0. But Mr. Poyer, it's not moving out there. How can it be accelerating? You do not have to be moving to be accelerating. That position to the far right and far left is the area of greatest acceleration, and it's also the area of 0 velocity. Think about free fall. When you toss a mass in the air, you have acceleration up at the top, but you don't have velocity. So they're completely different concepts, and hopefully that's okay. And then when is it in equilibrium? Well, let's think back to our definition of equilibrium. Equilibrium in physics is when you have a net force of, hopefully you remember, an F net of 0 newtons. When does an F net of 0 newtons occur in an oscillating spring? When you're back at the equilibrium position. When your x equals 0, when you put that into Hooke's law, you will get an Fs of 0. Therefore, it's an equilibrium. We'll pick it up here tomorrow.